Okay, class, welcome to Chapter 1. This is the second lesson in Chapter 1. We're looking here at atomic mass, and this lesson is going to help you understand how atoms are massed. And because atoms are very small and very light, and the particles inside them are even smaller and lighter, we need a system to be able to work with larger amounts. And this is sort of where we're working towards, is being able to work on the gram scale, or maybe the milligram scale, because of the way we do chemical reactions. We're quite often measuring out masses on that level. Certainly not trying to measure at atoms. So the first thing we need to understand is that chemists are very precise in their work, and instrumentation allows us to make precise measurements. And one of the uh, measurements that has been made on elements is that the mass of a given form of an element called an isotope can be actually separated or distinguished from other forms of that element. Let's take, for example, magnesium. When we look at a periodic table, we see lots of information on the grid. We see the atomic number, which represents the number of protons and the number of electrons. The electronegativity, we've examined that as well. Common ion charges and other ion charges. We see other properties such as physical melting and boiling points and density. But in addition to those, we see a number on the periodic table quite often, which is something we need to understand. And this is what's called the atomic mass. Now here it's called molar mass. It represents the same value, but it corresponds to a slightly different quantity of sample. But for now, we want to understand what this number represents. So if we look at magnesium, we see that a mass spectrum of magnesium, which is shown here, it's a graph showing percentage abundance versus mass number. Tells us that there are three dominant forms of magnesium. There's magnesium 24, magnesium 25, and magnesium 26. And of course, these are the isotopes of magnesium. They're all magnesium. They all have 12 protons and 12 electrons, but the number of neutrons can differ. In some cases it can be 12, in some cases it can be 13, in some cases it can be 14. Now when we look at this graph, we see that about 80% of magnesium, when analyzed, is found to be this magnesium 24. 12 protons, 12 electrons, but 24 subtract equals 12 neutrons. Now, about 10% each of these isotopes, magnesium 25 and 26, are also part of a sample of magnesium. Those would have respectively 13 and 14 neutrons. So these are heavy particles and they need to be considered in our chemistry, but certainly chemists can separate out these different isotopes. Okay, now let's have a look at standard atomic number. Standard atomic number is sort of a notation that we use, or standard atomic notation is a way that we represent elements. And here, some of the information we've already been talking about is represented in this form. So when I talk about the magnesium 24 and 25 and 26 isotopes, I'm referring to the mass number, okay? So we use the symbol A, capital A, which represents the number of protons and neutrons. This is the mass number. Below that is a smaller number, which would represent the atomic number, which is just the number of protons, or we could think of it as the number of electrons for a neutral atom. So those two numbers here allow us to distinguish isotopes. So here we have two isotopes of carbon, carbon 12 with a slightly different notation, and carbon 14, where that notation only shows us the mass number. But standard atomic notation represents all the particles in the atom that have noticeable mass, okay? So make sure we understand those forms. So let's just get a couple of definitions recorded here. So let's get out a definition for isotope.
All atoms of the same element have the same number of protons, but may vary in how many neutrons they have. Atoms having the same atomic number but a different mass number are called isotopes. Hydrogen has one proton and no neutrons. Isotopes of hydrogen may contain one or two neutrons.
Okay, so what are we talking about here? A form of an element, all forms differing in the atomic mass, but having the same number of protons and electrons, which is what's necessary for it to be the same element. Different number of neutrons is what we really need to take notice of when we're referring to an isotope. So, for example, oxygen 16 and oxygen 18 would have masses of obviously 16 heavy particles and 18 heavy particles respectively, but the O16 isotope would have 8 and 8, totaling 16 heavy particles, 8 protons, 8 electrons, and 8 neutrons. And the O18 isotope would have, again, 8 protons, 8 electrons, but 10 more heavy particles, giving it the 18 heavy particle total. Okay, so again, calculating the number of neutrons, N, is a simple matter of knowing your mass number and subtracting your atomic number. Okay, so if you have it in standard atomic notation, we can just subtract the lower number from the higher. Okay. Okay, so on this web page, just dramatizing isotopes, and they call it deuterated ice cubes, which means that the ice has been made from deuterium, which is a certain form of hydrogen containing a proton and a neutron, and that makes it twice as heavy, roughly, as every mass or every atom of regular hydrogen, which only has 1 proton and 0 neutrons. Okay, so there, as we just reloaded that page, you see the quick animation. We have 2 ice cubes being dropped in. The one on the left would be regular water, which has less density than liquid water and it floats. And the one on the right, obviously, is a ice cube made from a special type of water, which would be D2O. And because deuterium is, we could call it H2, but sometimes its symbol is D, we could write the chemical formula for heavy water is D2O, and then that would of course be a little bit heavier than regular water, H2O. This is going to sink in H2O liquid, and this floats. In liquid water. Okay, so one sinks, one floats. So there again, there's some evidence for the existence of isotopes. Okay, here you're looking at a chart which is looks a little intimidating at first, but what it really is just the atomic number on in the first column, okay, which is just the number of protons. It's the name of the element. In the second column, the symbol for the element, which is kind of a hybrid of standard atomic notation and the other notation, which just shows the mass number. And then we have the mass of the atom in a particular unit called the atomic mass unit. And then we have the percentage abundance. So if we just focus for now on this percentage abundance value, these are tabulated for us so that we can know that when we're referring to a particular element, let's say nitrogen, that nitrogen is almost all nitrogen 14. It's almost 100%. If we were to look at fluorine, fluorine doesn't have any isotopes. 100% of fluorine is fluorine 19. But if we were to look at an element like calcium, calcium has, well, let's say about 6 isotopes here that are listed that have percentages that can be measured. Almost all of it is calcium 40. We have next closest abundance would be calcium 44 at about 2%, and then it sort of tapers off from there. So this is a useful table that chemists can use if we want to know the breakdown of the different forms of an element. All right, returning to our other slide here. All right, returning to our other slide here, the second definition we want to add based on this discussion is what atomic mass exactly is. So it's obviously the mass of an atom, but when we refer to atomic mass, we're actually really describing the relative atomic mass. Now, atomic mass is, since the mass number is A, we use the letter A for mass number, and it's describing heavy particles, which are pretty much all of the mass of an atom. We use AR, Now it's not in here, but we can add that. So A subscript R is relative atomic mass. Now this is not the total of protons and neutrons, but this is a mass which is on a scale that's relative to a particular isotope. So rather than trying to say, well, the mass of an atom is so small, it's in grams, and there's a lot of zeros before the first digit, what we do is we refer to relative masses, where we say, okay, carbon 12, C12 has a mass of 12 atomic mass units. So it's sort of an arbitrary choice. Kind of fits because, of course, it has 6 protons and 6 neutrons, carbon 12 does. So if they're each assigned a relative mass of 1, then we total up all the heavy particles and we'd have 12 mass units. The electrons are so light that they don't contribute very much. So again, on this scale, a atomic mass unit, one atomic mass unit is just 1/12 of a carbon 12 atom. Okay, so the carbon 12 atom has 12 U mass value, and 1 U is just a 12th fraction of that. Okay, so one of the handouts you have in your package also is practice questions on, we're just working with standard atomic notation, so maybe this would be a good time just to make sure that you're feeling confident with how that works. So again, it was the symbol of the element, which is X, and then up above is the atomic, the mass number A, and then down below is the atomic number Z. So when we're working with number of neutrons is equal to the mass number subtract the atomic number. So if we had, for example, carbon 14 has 14 heavy particles, so its mass number is 14. Carbon is element number 6, so its atomic number has to be 6. The symbol in standard atomic notation would be C 14(6), and the number of protons is the atomic number, which is 6. The number of neutrons would be 8. Okay, so we'll work through that in class tomorrow. All right, coming back to this first slide, I just want to finish off with this this statement that when we look at the atomic mass on the periodic table, we're going to see a lot of decimal places in these values, almost exclusively. So I want to just explain what is going on with these values. Now, these are relative atomic masses, so they're relative to carbon 12. However, they're also averages. So when we look at, for example, iron, we're not saying that iron is 55.85 on a scale where carbon 12 is 12 exactly. We're saying that the average iron atom is 55.85 units. And because iron has isotopes, and if I was to go to a chart for iron and try to locate it, we see up above, 92% almost is iron 56, and then about 6% is iron 54. So about 4 isotopes, and they all have pretty noticeable percentages. So that means that when you average all the possible forms of iron together, you get this average value of about 55.85. Okay. Now, how exactly do you do this calculation? So it's just it's a weighted average. So I'm going to go to this last worksheet here and just go through one example, and then in class we can work on this some more. So how do you calculate the average atomic mass? Well, you need to know what the isotopes are and how heavy they are, and you also need to know their percentage abundances. So a chart similar to something like this, or something that could be accessed on the internet. Okay. So you have your chart, you know your percentage abundances. So 79% of all magnesium is magnesium 24, 10% is magnesium 25, and about 11% is magnesium 26. To come up with the average atomic mass, well, if we were to look at a periodic table, we would find that the average atomic mass of magnesium is listed as 24.31. So let's see if we can get something pretty close to that. This is sort of the relative atomic mass, and it's an average, 24.31. Atomic mass units for magnesium as an element. Now, normally if we took, say, 3 marks on a semester and they were all equal in their weight, we would just add them up and divide by 3. But in this case, the relative weight of each isotope is different. So we actually have to use, instead of a third, we have to actually use 80%, or about 79% magnesium 24. We're going to take 79% and we're going to multiply it by the mass of that isotope. And we're just going to add all these percent abundances. So 10% coming from magnesium 25 and 11%, 0.11, coming from magnesium 26. Okay, if we were to take that, we could do the math on it, get our average atomic. Okay, so I get actually 24.32, which is really close, which tells me that, okay, so that's pretty reliable. That's how we calculate the average relative atomic mass. If you're struggling at this point to try to figure out how these terms all give the average value, consider just something simple like two test scores where they're both equally weighted. So you have, say, a test score of 75% and a test score of 60%. And if I said, what's your average? You would obviously take 75 and you'd add 60 and you'd divide by 2. Okay. Now another way of doing that would be to say that half of your mark, or 50% of your mark, is coming from the score of 75, and 50% or half of your mark is coming from the score of 60. And this here, 75 and 60 divided by 2, would give us 67.5 as an average percent on your term so far. And of course, you get the same values if you took half of 75 and half of 60, which is 30, and added them together. Okay, you'd still get 67.5. So the key with this calculation is that you're using the percentage weight of each form or each value and multiplying it by the actual value itself. Okay, so I don't want to give a formula here. I think it's just simple to say that if we take the percent abundances for the different isotopes and multiply them all by their respective masses, add them all up, we'll get the average relative atomic mass. So if I do one more here just to give you some confidence with how this works, let's look at number 3. Okay, so again, 92%, 0.92 multiplied by its value of 28 atomic mass units, 5%, 0.05 times the silicon 29 isotopes mass, and 3%, 0.03 times the last heaviest isotope of silicon. Add them all together, we get 28.11. And if we compare that to silicon, it's very close. 28.09 is the listed value in the back of our textbook. So again, this worksheet will also finish in class tomorrow. Okay, so the video is closed now. At this point, just remind you that tomorrow we're going to be working on the practice questions worksheet 1.3a, as well as the calculation sheet that I was just looking at. There are some additional questions which we'll go through in the textbook, which are found on the bottom of this handout, found on pages 29, 32 in your textbook. So just encourage you to take it slowly with this and have patience. There is going to be some math in this course for sure. That's to be expected. And the calculations, they're not difficult formulas to really work with, but with a little bit of practice, we'll be able to get through this. So come tomorrow with the questions and we'll work through this together. See you tomorrow.